So what did we do last time? We started looking at random variables. Yeah. And what is a random variable? Okay, so what is a random variable? We had a very slightly sophisticated definition. It is yeah. So random variable is a function. There is nothing random about random variable in some sense. It is just a function which goes from the sample space to real numbers. There's nothing more than that. Okay, there is a sample space here. There's a real number line here. And for every element of the sample space, it will give a real number. That's what a random variable is. Yeah. And once you have defined a random variable, there are a lot of interesting events that we can define. Yeah. We can define the event which is random variable equal to, let's say, 1. What is this? This is a subset of the sample space. What is the subset of the sample space? This is the set of all w belonging to omega such that x of w equal to 1. This is a subset of the sample space. Everybody agrees? Yeah. And this particular subset is an event and that has a probability. Yeah, and that's what we mean by this notation. Okay, this is some notation to define the subset. So once we have this notation, we can do interesting things. We can say, okay, what is the event that the random variable is between 1 and 5? Yeah, this is an interesting event, and we can define the event very easily. So the random variable we took as example last time was, let's say you are throwing dice 10 times, and what is the number of times the number 3 came up, right? And this is the event that the number of times the 3 came up is between 1 and 5. Yeah. So that was it. And we also looked at the binomial probability distribution. Yeah. So we will see it again in the next slide. So yeah. So we also defined a function called probability mass function. Okay. So last time's lecture, I called it probability density function. There is a correction, so that should be called probability mass function, not probability density function. Yeah, so that is called probability mass function. So any random variable x, it is denoted like this. This is nothing but the probability that the random variable capital X equal to the value small x. Yeah, so this is called the probability mass function. Yeah. And for the number of heads coming up, this worked out to be probability of x equal to x. So let's say it's a binomial distribution with parameter n, and p is the probability of heads. This was equal to n choose x, p raised to x, 1 minus p whole raised to n minus x. Right? We saw this formula. We also try to explain how this formula comes. Yeah. So we also try to explain how this formula comes, and we also talked about what you mean by expectation. Yeah, which is kind of the average value of what a random variable is, and yeah, so we said that the average value for binomial distribution was NP. Yeah, we didn't prove that, but we'll be proving it very soon. Okay. Okay. So let's continue. Yeah. So always the random variable will be a capital letter, and the value that the random variable is set to will be a small letter. Okay. So this is a very common notation. Is there any questions? Okay. Yeah, so we already saw this probability mass function. Again, last time we called this probability density function, and that was wrong. This is called probability mass function. There will be something else which will be called probability density function, which will be coming up later. Okay. Yeah. Yeah. So let's look at another example. Okay. So let's say you are interested, you are tossing the coin n times. Yeah. So you are tossing coin n times. Yeah. And we are given that the probability of heads is let's say p. Yeah. Now let's look at the random variable. Number of times okay, times to toss to get the first hertz. Yeah. So how much time should I wait? How much time should I keep on tossing such that I get a head? Yeah, and that's a random variable. Yeah. So yeah. So for example, let's say the random variable is a function. Yeah. So here the sample space is. What is the sample space here?
Natural number.
0 to n.
1 to n.
Yeah. Sample space is all possibilities. 0, 1 raised to n. Sample space is something very simple. It is the number of all possibilities of the experiment. That is, if you have n tosses, there is, each tosses can be head or tails. 1 means heads, 0 means tails. Yeah, and there are 2 raised to n possibilities. That is the sample space. Sample space is always simple. It is the number of all possibilities. Yeah. Yeah. And x is a function which maps this sample space to real numbers. Yeah. And what is the value of x? So x is x of 0, 1, 0, 1, 1, 1, 0, 0. Is there yeah, let's say there is a, this is n is equal to 1, 2, 3, 4, 5, 6, 7, 8. N equal to 8. Yeah, so what is the value of this? Yeah, so we said x is the number of times. So it is 2. So I have to wait for the second toss for it to become head. So somebody said 4.
Yes,
so
sir.
why is it 4?
Because in that series we are getting 4 heads, and our requirement is a number of okay,
So
tosses to get the first.
what is the definition of x?
Okay. It is
Yes.
number of tosses to get the first head. Okay.
Yeah, number of times you need to. I change the function. Yeah, so you need to read.
Yes.
Number of times to toss to get the first hertz, and this has happened in the second place. Yeah. And,
Yeah.
So if I had 0, 0, 0, 1, 1, 1, 1, it would be a 1. Okay, maybe one more 1. It would be a 4. So everybody is clear what the random variable is. Yeah. Yeah. So now let's write the probability density function of this random variable. Yes.
Explain this part once again.
Okay. What is the random variable? It is the number of times you should toss to get the first hertz. Is that clear?
Yes.
So you toss, you are not getting head. You are toss, you are not getting head. So how many times should I keep tossing to get the first head? Yeah. So suppose you tossed 8 times. Yeah. And this is the sequence of occurrences that you got.
Yes.
Yeah. When did you get the first head? At the second position.
Okay. Yes.
So that's what this random variable is saying.
Okay. Yes. Thank you.
So this is yeah, x is the number of times you should wait for the getting the first head. Okay. Now, okay, we have defined a random variable. Everybody knows what the function is from the sample space to real numbers. Everybody knows. Now, yeah, what is the probability mass function of this? What is the probability that x equal to k. So we are working in the n case, okay, n and p, okay. So this is yeah, formula says that this is the probability that x equal to k. Yeah. So what is this probability? What do you think?
1 minus p की power k minus 1 into p.
Is that clear to everyone?
Yes, sir.
Yeah. And if you have, so which are all the occurrences? This event will have strings where the first k minus 1 bits are 0 and the kth bit is 1.
Sir, why we are subtracting 1 minus p? Can you explain a bit?
Yeah. So what is this event? Could you tell me what are all the elements of the sample space which satisfies this?
The first element should be 1, right? Like the other elements can be other digits.
What do you mean by x equal to k?
A probability of
Okay, what is x?
Uh,
What is x? Do
sir-
we agree on
sir-
what x is?
Yes, it is in the second time, in the second experiment, we got the first head. So how it will be 1 minus p whole power k minus 1 now? It is not the number of heads, right?
So what is x? It is the number of times you need to toss to get the first hertz.
Okay.
You agree?
Okay. Yeah, I got it,
So,
sir.
what do you mean by x equal to k? Which are the, so there is this sample space and there is a subset which satisfies x equal to k. So what is that subset of elements which satisfy x equal to k? Yeah.
So,
If it has to substitute x equal to k, then the first k minus 1 bits has to be 0.
yes.
And the kth bit has to be 1. And the rest of the n minus k bits can be anything. We don't care. You agree?
Yes, sir.
So this k minus 1 bits has to be 0. The kth bit has to be 1. And the rest of the n minus k bits can be anything. We don't care. Yeah. And how many elements, and what is the sum of probabilities of all those elements? So these are independent trials. No? The coins are independently tossed. So here it has to be 0, that is 1 minus p. Here it has to be 0 into 1 minus p. You have to multiply 1 minus p k minus 1 times. Then you have to see a 1, that is p. And then we don't care. Is that clear?
Yes, sir.
Okay.
Excuse me, sir.
Yes.
Sir, what will be the value of x in the event when we get all zeros for all the n tosses?
Yeah. Anybody want to answer that?
Infinite.
Yeah. So it's not clear. Yeah. So yeah, in that case we will. So the function is not well defined. So then we need to say that okay, then the value of x is n plus 1. Something like that we will have to say. Okay. Or infinite as somebody else suggested.
1 minus p की power n.
Sorry.
If all are 0, then it will not be that 1 minus p की power n.
No. He is saying what is the value of x of 0 raised to 0, 0, 0, 0, 0. What is the value?
All are 0, so 1 minus p की power n.
That is the probability. I am asking what is the value of the random variable function.
Okay, value.
Yeah, so as he said, it's not well defined. Yeah, so typically, yeah, we don't know what the way I talked about the random variable. It's not clear what I should give. the value of the random variable is in this case.
Should be zero because there are no heads, no?
Yeah. So what should I give the number here? I should give the random variable should be defined for every element of the sample space, right?
Right.
It has to be defined for every element of the sample space. But for this particular element in the sample space, what is the value of the random variable? That's what Sumit was asking.
It should be zero, no, because there are no heads, no?
Okay. I mean, so you are saying this. So what about this? This is also zero.
Huh. Okay, right. Sorry, got confused.
Yeah, it's a very important question what Sumit raised, in fact, actually. So the way I defined random variable, the value of the random variable in this case is not well defined. So typically there is no n parameter here. Okay. So you will keep on tossing. Okay, toss coin infinite times, countably infinite times. Okay, you keep on tossing coin one after the another, yeah, and you are trying to get a heads. That's what you are going to do. Yeah, everybody understood? You keep on tossing heads and yeah, waiting for a head to come up. Yeah, and yeah. So yeah, so when I write the string, what I mean is the rest of the elements we don't care. Okay, in some sense. Okay. I mean, we don't take any string with any suffix. This will be still be equal to 2. Okay. So in that case, yeah. So this is not well defined. You should also give the substring after this 0. Then only this is well defined. Okay. Yeah. So what else? Yeah. So we have the probability mass function. Yeah.
Excuse me, sir.
Yes.
Sir, in random variable, when the string was all ones, why the value was not 1, which you have just deleted?
It is 1. I didn't say it is not 1. It is 1. Yeah, it is correct.
Okay.
Yeah. Okay, so we have seen what this is. So what is the expected value of this random variable? On an average, how much should I wait for seeing a head?
Summation of k into p into 1 minus p raised to the power k minus 1.
Yeah, summation over x, x times. So x belongs to natural numbers. You could toss, you are choosing infinitely.
Yes.
Px of x. This is the formula.
Yeah.
So let's substitute summation over x belonging to natural numbers, x times yeah, that particular thing, 1 minus p whole raised to x minus 1 times p. Yeah. So what do you do now? Yeah. So what do you do now? So there's a p common, I think, everywhere. So I can take the p out of the summation. X equal to, x could start from 1 to n, 1 to infinity. Yeah. So how do you compute the summation? Anybody has an idea? Arithmetico-geometric progression. But yeah, there should be a simple trick to do this.
It's like differentiation.
It's like differentiation. Why is it differentiation? Yeah, but how do you solve this? Like, this is a summation. How do you solve this? Yeah, so yeah, so does anybody know how to solve this? Okay, expand series, call that yes. Okay, so this entire series is, you are saying this entire summation is yes. Okay, and then subtract it from s into 1 minus p. Okay, does Abhiram want to explain that?
Hello.
Yeah.
Am I audible, sir?
Yes, yes, please.
So we'll be calling that. So if we substitute that, we'll be getting 1 minus p power 0. So it 1 plus 2 into 1 minus p plus 3 into 1 minus p square plus so on. We'll be getting and we'll be considering that as s.
Okay, so you are taking x equal to 1, then this is just 1. X equal to 2, this is 2 into 1 minus p.
1 minus p plus
3 into 1
3
minus
into 1 minus p square plus so on.
So on, yeah. So let's call
And
this
then
yes.
we'll be yeah.
Okay.
So we'll multiply s into 1 minus p now below.
S into 1 minus p you want to write. Okay. S into 1 minus p I have to write. Okay.
Yes.
And that will be
and then,
1 minus p plus 2 into 1 minus
2
p
into 1
squared.
minus p square plus so on.
Okay.
And then subtract them. We'll get gp.
I see. So let's subtract this. Okay. So we will subtract this term from this term and so on. Yeah.
Yes.
And yes, minus s into 1 minus p is so yeah 1
plus 1 minus p plus 1 minus p square plus so on.
Great. Yeah, it's an interesting trick. So 1 minus p the whole cube and so on, and that is a GP.
GP, yeah.
And that is a by 1 minus r, infinite GP, no? So
yes,
1 minus 1 minus p is going to be p.
1, yeah.
Yeah. So s into 1 minus p is going to be the s gets cancelled.
SP.
This will be sp. Yeah. So s is equal to 1 by
1 minus p, 1 by p square. Yes.
Yeah. So s equal to 1 by p squared. So s became 1 by p squared. Yeah, so what is this?
This is the expected value. I mean, we.
Yeah. So I substitute s to be 1 by p squared here. The 1 p get cancelled, so it is 1 by p.
Yeah.
Yeah. Is that clear to everyone? Yeah. So let's say the probability of getting that heads is very, very small. It is 1 by 1000. Yeah. Then you need to wait for 1000 steps to see a head on an average. If it is 1 by 10,000, very minute probability of seeing a heads. Yeah. Then you need to wait for even longer. Right. So yeah, that's what. Okay. So. Okay, so it's always good to actually work things out from first principles. Okay, so yeah, maybe this is AGP, there is a formula, but just don't accept formulas. You just try to work it out from first principles, because this method can be used to solve many problems, and this is a common method in probability. You will see that many other problems can also be solved using this. So if you know this method, you can solve a range of problems. If you just know the formula for AGP, you will solve this problem, but in the other problems you will not, it will not help you. Okay. So this particular this particular probability density function, any random variable this particular probability density function is called a geometric random variable. Okay. Any random variable which has the probability mass function like this is called a geometric random variable. So we now saw you two kinds of random variable. One was the binomial random variable, which is you are counting the number of heads, and other is called the geometric random variable, which is how much should I wait to see a head, right? So let's go back. Yeah. So let's see another question. Yeah, so let's say you have a four-sided dice. Okay, this was the dice which was used in ancient India. It was like a long tubular thing. It had only four sides. That corner points was never there, and you just roll it. Yeah. So I mean, yeah. So you had that kind of dice, and it has four sides. Yeah. So you throw one, and let's say I mean both the dice are distinguishable. Yeah, and you are throwing two dice. F is the outcome of the first throw. S is the outcome of the second throw. Yeah. So both F and S are random variables. Are these random variables? Yeah. Anybody has a doubt that this is not a random variable? Yeah. Because the sample space is yeah. I mean x comma y, where sample space is x comma y, where x comma y is belong to 1, 2, 3, 4. Yeah, and yeah, f is the outcome of the first row. So f of xy is just x. Yeah. Similarly, s of xy is just y. It's a random variable. It's a function which maps omega to real numbers. Yeah, this is a x and y are real numbers. It is a number 1, 2, 3, 4. Yeah, so it's a perfectly valid random variable. Now, given two random variable, I can apply the minimum function on it. Yeah. So yeah, I can apply functions on random variables. So here I'm just applying the minimum function on f and s. Yeah. So I'm defining a new random variable. And this is the beauty of random variables. Once you have a random variable which is a real number, which is mapping to a real number, you can also consider compositions of random variable, and they will be random variables. For example, I can define the random variable which is f times s. What is f times s? It is the random variable. So f times s of xy is the random variable which is x times y. Yeah. So this is the reason why we typically think in terms of random variables. Once we define a random variable, you can compose them, you can multiply them, you can add them, you can divide them. Yeah, you can take their minimum, you can take their maximum. You can ask the question whether random variable is in a particular interval. Yeah, all those interesting questions you can ask because you defined a random variable. These questions are very difficult to ask in terms of the original sample space. Okay. So yeah, that's why we have a random variable. Now, yeah, so yeah, what is the probability? Yeah, mass function of x. Yeah, what is the probability that mass function of x? Yeah, so this is the probability that x equal to 2. Yeah. Now, when can x be equal to 2?
Excuse me,
sample
sir.
Space? Yes.
So, can you explain how again f and s are random variables?
So I have defined f and s here, no?
So f is the outcome of the first row, right?
I am defining f as a random variable. What is the sample space? You agree that this is the sample space?
Okay. Yes. Yes,
You
got
agree?
it. Got it.
Yeah.
Got it.
And f is the function which maps omega to real numbers. Yeah.
Yes.
And
Yes.
for any tuple x comma y, f is the function which just gives the first value.
Okay.
And s is the function which just gives the second value. So they are random variables. They are a function from omega to r.
Yes, sir.
Yeah. So yeah. This is the thing about mathematics. You need to think. Start thinking in terms of mathematics. Okay. In terms of English, many things doesn't make sense. You think clearly in terms of math, it start making sense. And none of this, what is being said, is complicated or anything. There's no complication here. We are
Sir,
just making things well defined.
Sir, but what if the outcomes of the dice were A, B, C, D instead of 1, 2, 3, 4?
Yeah, then you cannot do this. Then this doesn't. It won't be a real number. I agree.
Okay.
But I defined my sample space like this.
Okay.
I defined my sample space like this, and then only defined this, right?
Yes.
So yeah, the definitions are very important. Yeah, and that's why I defined it like this. That x, y is a number in 1 to 4. Yeah.
Okay.
Yeah, if it is some other A, B, C, D, then you need to map A, B, and C into some some numbers, and then you have to move forward.
Okay.
Okay, so that is good. So min of fs is also a random variable. Everybody agrees? Min of fs is also a function which maps the sample space to real numbers. Everybody agrees? Is there a confusion?
No, sir.
Yeah, great. So what is the probability that this random variable x equal to 2? Yeah, so this is the sample space. So when or can x be equal to 2? So suppose this element in the sample space, can this be part of this event?
No.
This
No, sir.
cannot be. Okay. So can this be part of this event?
No.
So this also cannot be part of the event. Okay? What about this? Can this be
Yes.
part of the event?
Yes,
Yes.
sir.
Yes.
Okay, this
Yeah.
is part of the event. What about this?
So cut out the
No,
last
sir.
row and first column.
Okay, so this is also not possible. And this looks like a symmetric figure. Yeah. So what
Yeah.
about this? What about this? Symmetric. Yeah. What about this? And this is also fine. What about these? Yeah. This area?
No, sir.
Everybody agrees that this is also no? Yeah. So how many possibilities are there? 1, 2, 3, 4, 5.
9.
Yeah. Okay. So is there any questions? Is there any doubts regarding this?
So can you explain the definition once more? Means why is it mapping to set of real numbers every time?
So you are saying y is f and s a random variable, is that?
No, sir. Means from sample space, why is it every time mapping to set of real numbers? I'm a bit confused here.
No. Our definition of a random variable is it's a function from sample space to real numbers.
Okay.
That is our definition. And the question was, is f a random variable? Yeah. F was a random variable. Take any element of the sample space. It is giving the first number, and a number is a real number.
Okay.
Similarly,
So it
s
is.
is, yeah.
Yeah. So it is because f and s are random variables. For that reason, x is also getting defined like that as a random variable.
Yes. That's why we move to random variables, because once you have defined some random variables, you can multiply those random variables. That's again a random variable. You can multiply two functions. That is another function which maps the sample space to real numbers. That's again a random variable. You can add two random variables. You can divide random variables. You can take the exponential of random variables. You can take the logarithm of random variables. Yeah. So all these manipulations we can do in the random variable world. This all this will not make sense in the original sample space. If we just work with the original sample space and did probability like what we did in the first section of the course, we won't be able to talk about many interesting things. But once we move to random variables, you can do a lot of mathematical operations on them. And that also is practically very useful. We will see there are a lot of practical problems, all this operation we need to do. Okay. Yeah, and calculating probabilities in the random variable world is going to be a little bit complicated. One way is you go back to the original sample space world and do the calculation. Other thing is typically all these random variables follow some very well-known distribution. Yeah. So we already talked about two distributions. One is the binomial distribution, and it's the geometric distribution. Yeah. So let's say you're tossing dice. How many times should I wait to see the number 6? That's a 6-sided dice. Yeah. So you already know how to compute the probability for this. You already know what the expected value of this random variable is.
Yes.
Yeah. There's a formula for that. Yeah. So when you talk about random variables, typically the probability mass function of the random variable will be very well known. And once we know the probability mass function, there will be a standard formula for the mean for a typical events that we want to compute. Yeah, that is the advantage of random variable. We don't need to go back to the sample space and do a lot of calculation all the time. Okay. Yeah, so this we already saw the binomial PMF, and we also saw what do you mean by expectation. Okay. Yeah, so this is some properties of this expected value. Okay, this we didn't see last time. Yeah. So we already saw that we can take functions of random variables. So suppose you have a x as a random variable, I can define a new random variable, which is a function of the original random variable. Yeah, and only thing is g must be a function from real numbers to real numbers. Yeah, as long as g is a function from real numbers to real numbers, g of x is also a random variable. Everybody agrees? Yeah. Take any function from real numbers to real numbers. Yeah, you apply g on a random variable. That's again a random variable. Yeah, because the random variable already converted the sample space to real numbers, and then you are applying g, which converted real number to another real number. So it perfectly makes sense. Okay. So y is also a random variable. Okay. Now you can try to find the expected value of y. Okay. How do you find the expected value of y? You just put the formula. Yeah. But what is py of y? Yeah. So how do you compute py of y? Yeah. So maybe we know x is some well-known probability distribution. X is a well-known random variable. Okay, let's say it is some geometric or binomial or something like that. So we know everything about x. We know how to work with x. Yeah. Now yours y is, let's say y is something like, let's say, okay, x squared plus x minus 3. Y is a random variable. Yeah. So what is the probability mass function of y? How do you compute the probability mass function of y? What is the probability of y equal to y? Yeah, could you give a formula for this? Let's call this function g also, g of x. Anybody has an idea how to compute the probability mass function of y?
Using integration.
Using integration, okay. Why do we need integration here?
Because x is a continuous variable.
Okay, let's say x is either number of heads or or the first time to get a head. So it's a discrete random variable, no?
Okay. I'm now.
So we get G inverse y, we will be getting the value of x, and we know the distribution of x.
So what Varun was saying was, you sum over. I think Mahak was also saying something. We will soon come to integration also. But for now, we are looking at discrete random variables only. But what Mahak said was also correct in some sense. We will come to that at a later point. So you look at all the values of x for which g of x is equal to this particular small y. Yeah. So if the random variable x took any of those particular values, my random variable y would be equal to the small y. Do you agree? Yeah. And for all of them, you just is this formula clear? So you had the random variable x. So this is the sample space and this is the real numbers. Yeah. So you have the random variable x, which is mapping the sample space to this real numbers. Yeah. And then you have a function g, which is mapping real numbers to real numbers. Yeah. It might map multiple real numbers to the same real number. Nobody said g is a 1112 function or anything like that. It might map multiple real numbers to the same real number. Yeah. And in particular, this particular function, what is the graph of this particular function? Yeah. There are multiple values of x for which the same y occurs, right?
Excuse me, sir.
Yes.
Sir, in the formula of this expectation of y, why we are not multiplying with y also in the summation?
It is. We are multiplying y also here. I'm saying, how do you compute py of y?
No, sir, in the right side, in the box which you have written.
But here I didn't write expectation, no? I just said what is py of y?
Oh, okay, I got it.
I'm just saying, how do you find py of y? If I have to use this formula, if I have to find py of y, yeah. Question is, how do you find py of y? Let's say x is a well-known random variable. It's binomial, it's geometric, and we know how to deal with that. We saw examples. But this is some complicated function of that initial random variable. Then how do you compute py of y? Yeah. And the way to do it is this. Look at all the values such that this function maps to the same output. So this is that is a quadratic thing. So it might look like a parabola or something. So if this is x and this is y, it might look like a parabola or something. So there is two values of x which maps to this particular value of y, right? So if I want to find the py, the probability that y equal to small y, I have to add the, so this is, let's say, x0 and this is x1 and this is y. So the probability of y equal to y is probability of x equal to x0 plus probability of x equal to x1. Everybody agrees?
Sir, I have a doubt.
Yes.
So in expectation, you said that we have to multiply like y with probability of y, and we have to sum it up.
Yes.
But in case of dice, let's say we want to find the expectation of getting a 6, right? So we will multiply 6 into 1 by 6, and that is like expectation.
No, what is your random variable? What is your random variable first?
To get a 6, to get a 6.
What do you mean by to get a 6? What is the random variable? Is your give me the function when from sample space to real numbers.
Can I say like if I roll a dice, then at least I should get 1 6. Like if I roll the dice 2 times, so
No, you need to give me a function from sample space to real numbers. Yeah, I mean, then only we can talk about random variables. What is the function from sample space to real numbers? Once that is clear, everything else will automatically become clear. But the thing is, what is the function from sample space to real numbers you are talking about?
It can be something like number of tosses to get first 6.
Number of tosses to get first 6. So what is your sample space? It is the set of all sequences, infinite length sequences, where every element is 1 to 6. Is it?
Yeah.
Okay. So we understand the sample space. It is the infinite sequence where every element is 1 to 6. And what is the random variable? It is how many toes should be there to get the first 6.
Yes.
Okay. So what is the probability mass function of this random variable? So everybody understands the random variable, no? Give me any long infinite length sequence. Look at the where the first 6 appears, and that's the value of the random variable. Yeah. So the function from sample space is first clear. Then the function from sample space to real numbers is also clear.
Yes, sir.
Yeah. And then you can now ask, okay, what is the probability mass function of x?
Yes.
Yeah. And the probability mass function is a geometric random variable where the parameter p is 1 by 6.
Correct.
Yeah. So
Sir,
yes.
Just one small thing. You have written here G maps from R to R in left top side.
Yes.
And you have written G of X is also a random variable. I just
Yes.
wanted to say, shouldn't we write G of X of sample space is also a random variable? X of sample space. Then only we'll get real number inside the G, right?
No. What is a random variable? Random variable is a function. Random variable is a function from omega to R. Right? Yeah. So so the name of this function is x.
Right.
Yeah.
So we should write X of sample.
Let me just complete.
Okay, sir.
So G is another function from real number to real number. Yeah. So G of X is also a function from real number to real sample space to real numbers. You agree?
Yes, sir.
Yeah. So how do you what is the name of this function? This function is called G of X. So G of X is a random variable. That's what I have written here.
Okay.
Yeah. Obviously, G of X is a function from sample space to real numbers. That everybody knows.
Okay, sir.
Okay. Fine. So yeah, what we just now described, what do you mean by a function of a random variable? As long as your function is from real numbers to real numbers, that is one thing. Secondly, we saw that, okay, given the probability density mass function of the earlier random variable x, how do you get the probability mass function of the new random variable after applying the function? Yeah. So you need to sum up over all x for that the previous random, the the function is mapped to the x is mapped to y. So in this example, we draw the graph. Okay, so this is a quadratic function. So this is a parabola. So there are two values of x for which the same value of y is coming. Yeah. So the probability of y equal to y is probability of x equal to this particular x0 and probability of this particular x1. So for every value of y, I need to find this particular x0 and x1 and go on sum them up and get the probability y value of y. Yeah. So computing this is a complicated business. You need to solve some quadratic equation, find that x0 and x1 and then do this. This is a very complicated procedure, and that's why applying this formula is not a good idea. Okay, never try to do this when you have a function of a random variable. Yeah. So what you can do is, so instead of y, so another way of writing the same thing is this formula. Do you know how that formula is obtained? Why is this equal to this? Yeah, so you have summation of y times py of y. Yeah. Why is that equal to this?
We are finding all values for which gx equals to y.
Yeah. So we already have a formula for py equal to y. Let's substitute that. Yeah. And what is y? Y is actually equal to g of x. Yeah. So this is equal to summation over x g of x into px of x. Is that clear? Yeah.
Sir, could you please repeat after you substituted p of y with our summation formula?
Yeah. So in this summation, y is always equal to g of x.
Yes, sir.
Yeah. So I mean, yeah. So since y is equal to g of x, I can substitute y to be equal to g of x here. I can take this y inside. I can take that y inside, but y is equal to g of x inside summation. I'm just substituting y equal to g of x. Yeah, and now you have changed all the variables y to x. So you just need to sum over x. Okay.
Sir, could you also tell us how to distinguish between a binomial and a geometric random variable?
That depends upon the situation. I mean, everything is not numbers. You look at the problem. The problem will, so look at the problem and try to define what is the probability mass function. If the probability mass function looks like n choose k, p raised to k, 1 minus p raised to n minus k, then that is binomial. If the probability mass function looks like 1 minus p whole raised to k minus 1 into p, then it's geometric. Yeah, yeah, you need to read the problem, understand it, think about what the probability mass function is, and then you can say whether it is binomial or geometric. Yeah, I mean, yeah, you need to think. There is no like mechanical way of doing it.
Okay, sir. Thank you.
Yeah, you need to understand the situation and yeah, make a call. Okay, yeah, we are going a little bit slow. So one interesting consequence of this definition of random variable is, let's say the constant 2. you can think of the constant 2 as a function which maps any element of omega, okay, into the real number 2. So for all w belonging to omega, yeah, 2 of w is equal to 2. Let's think of this particular function which maps everything to the number 2. Yeah. So we will call that particular random variable a constant random variable. It's always a constant, just maps everything to that number 2. Okay, and as a simplifying the notation, we will call that random variable also 2. Yeah. So if you take a constant alpha, a real number alpha, you can think of the real number alpha as a function which maps all your sample space into the real number alpha. Yeah. And that's what we mean by, okay, a constant random variable alpha. Is that fine?
Sir, yeah. Is it like we have a coin and on both the sides 2 is written?
No. I'm just looking at the constant function. It maps all the sample space into a particular value alpha. So this is just a mathematical definition. This need not have a physical meaning to it. Okay. So as you said, as we said, like we want to translate into a mathematical way, and we would like to have some random variables which are constants, because that is helpful in manipulations. Yeah. So what is the expected value of a constant random variable alpha?
Alpha.
Yeah, because you take any of your sample space, it's mapped to alpha. So you essentially will do alpha times summation of all the probabilities, which is alpha only. Yeah. So if you do alpha times x, what happens? Right? Alpha, I can take out the summation. Is that clear? Yeah. Yeah. So the random variables are linear. So you can take multiply and add things, and the expectation will just go into it. Okay. So we will just stop there for today. Okay. So yeah, we are already over time. So thank you. So we will take questions today evening. There will be a 2-hour marathon office hours, because yeah, you couldn't we couldn't do it yesterday. Okay. Thank you for now. Do post questions in the discussion forum, and please try to also attend the harder questions in the discussion forum. Okay. Yeah. Thank you.
Thank you, sir.